Gratitude to the organizing team, Dr. Sachin, and the university for giving me the opportunity to be delivering a lecture in this important program. As you can see, I have chosen a topic for my lecture, which is on embedded machine learning for signal processing applications. I hope you have, and I could see that you have attended a number of other lectures, very, very important lectures on important topics, covering different aspects of machine learning, the fundamentals, the applications in signal processing, wireless network, IoTs, baseband communication, audio signal processing, and so on. So I have been understanding that you have had a wonderful, opportunity of understanding the machine learning concept thoroughly, and also how the machine learning concepts could help the signal processing applications to exploit the complete capabilities of signal processing usage. So as you can see one diagram here, one picture here, there is one device, there is one electronic system, or you can say electromechanical system, exploiting the ability of human brain. When we talk about machine learning is nothing but, it allows the computer or computing machines to mimic like human brain, to act, to behave, and to work like human brain. So the machine learning is one thing, and other is embedded machine learning. But before I talk about EML, that is embedded machine learning, I want to tell you one, introductory thing. This is being organized by Electronics and Communication Engineering Department. And see, the signal processing especially, the emphasis on signal processing has been tremendous in the last decade. Due to the emergence of machine learning, due to popular and huge usage of machine learning, the signal processing, the application has become abundant. You can find enormous amount of research on signal processing. You can also find the application of signal processing in almost all domains of science, engineering, technology, mathematics, economics, etc., etc. Because when we talk about data science, ML, or AI, there is always some flow of signal. There is something which is applied to some kind of signal. The signal may be a statistical signal. The signal may be an economical signal. The signal may be, related to the sentiment analysis of social media data. So the signal processing has become very, very powerful, employing ML tools, that is machine learning tools. Now, the background of this EML, for me to choose this topic as a topic for lecture is, for last 6-7 months, one professor from South Korea, Professor Kim, has been behind me, asking me, and actually he is submitting a research proposal of $1 million to an agency, UN agency. And he is submitting a proposal on smart health environment system. And when we talk about a smart health environment system, we hugely, require the use of IoTs, IoT devices, embedded devices, the role of ML and AI. So this is how I, thought of contributing on this particular topic, as this has become really very important, that we know that ML techniques, that is machine learning techniques, empower the capabilities of the different aspects of science and engineering. The empowerment is done. The fullest use of capability of science and engineering and applications can be demonstrated using machine learning techniques. But the EML is something different. So as you can see one diagram, another interesting diagram here, as I'm, being a person of image processing, I make full use of images in my lectures, the pictures. But I always give the credit from where I borrowed the images or the pictures. So the agenda of my lecture is divided into 4 important parts. I'll be talking about introduction to EML, embedded, then I'll go to embedded vision, TinyML and JOIS. And thirdly, smart sensing and energy efficient EML. And lastly, object detection using Raspberry Pi. As you know, one is simple example of how ML can be modeled and embedded into a device, and the capability can be explored. So as you can see that there is MLDR, that is deep learning or machine learning. There are this side embedded devices or IoT devices. But between the two, there is something called as TinyML, or there is some other, you can say package that allows running up machine learning, exploiting the machine learning capability in the device itself, in the small electronic system itself. That is where the EML, comes into picture. So when you say ML, when you talk about ML, as I have told you, ML enables all the electronic systems to learn the data, to capture the data and learn the data automatically. Huge amount of data can be, trained, and the understanding is developed by employing suitable machine learning technique. And then what happens next, you all know it very well. After understanding, training the data, we use using suitable ML technique, there is an acquirement of knowledge, and that knowledge base, because whenever we mention ML helps to train the data, to learn the data, to understand the data, to comprehend the data, and then it helps to acquire the knowledge. And that knowledge base is the basis for, many other post processing of signal processing. We always mention this term acquirement of knowledge, knowledge acquirement, development, understanding, representation of knowledge in different forms in artificial intelligence. So in different applications, assessment can be made, predictions are made, decisions are made. Wherever there is abnormality or anomalies, wherever there is uncertainty, all those situations are handled very, easily when we employ a suitable ML techniques. But we are talking ML techniques in context with the small devices, the powerful IoTs, where actually we want to exploit the ML, and we also want to, get the swift responses from the devices. So such applications which employ ML techniques, they are all highly computing intensive. You all understand very well. A lot of computations are required, and all those ML which are run on those systems, electronic systems, they all are executed on PCs and also make use of cloud servers. This is also possible to perform ML directly on devices. Now I'm going to introduce the term embedded machine learning. The embedded machine learning makes it possible that ML can directly be performed over the device. Rather than, if a device has a sensor, you see one diagram here, there are smart sensors in an application. The application may be robotic application. The robot, you know that in healthcare, especially during, pandemic, we have seen that a robotic kind of, the products were employed in different modern hospitals for different deliveries, different kind of deliveries during the treatment of the COVID-19. So the system becomes powerful with the help of intelligent sensors, these smart sensors. Whenever we call the sensors as smart sensors, they are all empowered by AI and ML. So what is important here is we have a number of devices, we have a number of electronic systems. Every time the sensors are capturing the data, but those data are subjected to, some cloud or personal computer where ML runs, the ML is executed, and then whatever decision comes back, whatever understanding comes back, accordingly, the device responds. If the robot has to move in certain direction, that decision making or understanding comes from the cloud-based server or the personal computer. So that makes dependency on huge dependency on the cloud or the PCs. So embedded devices which can perform many tasks in industries, as I told you, robotic, driverless car. There are many applications where we are going, for automation. We talk about smart home, smart environment monitoring system, where we have small devices, miniature devices, where miniature sensors are used. Such tasks which are performed in industries, they are also for everything, the dependency will be on certain computer or the ML. So that such as sensor devices which are used to detect acoustic, optical anomalies or any other type of signal that can be used to support the quality assurance in the industry during the production stages, or maybe to monitor the different stages or different conditions of system. So there may be different types of sensors which can be used for different purposes. And all those smart sensors capture the data, and those embedded devices, what we aim in the EML is those embedded devices, there itself, the decision is made. There itself, the prediction is made. There itself, we know the status of, the condition of the device. We can monitor the status and health of a device or a health of a certain environment. That is what, we intend to make it possible using the technique called as EML, that is embedded machine learning. There is another picture where you see that there are sensors and actuators. Actually, this is the scenario actually. Sensors and actuators are there in different applications. Some of the sensors are, connected in car, home, etc., different applications. Where the processing happens, communication happens through, using certain networks. And then there is a local area network, internet is there, by which the devices are connected through certain network. And there you have, some remote server. That server is connected through the internet to these all sensors and actuators, which are, present in the different applications. So what happens? The Internet of Things called as IoT is the main reason for, we talk about sensors. These days, everyone talks about data. Huge data. Huge data is there in the world, in the globe. We have data here and there, everywhere. And that data needs to be interpreted properly. If it is not interpreted properly, is meaningless. And therefore, why the data is increasing? As we know that in almost all applications of engineering and technology, we use different types of IoTs and electronic devices. They're all equipped with the number of sensors. You can talk about an ordinary smartphone where more than 22 sensors are there. In your ordinary smartphone, there are more than 22 smart sensors are there. So exponentially increasing number of sensors are there because of deployment of different IoTs. And those sensors are used to capture huge amount of data, which is collected by the embedded IoT systems. So of course, because there are huge amount of data which are captured by those devices, we want to interpret that huge amount of data using suitable ML. You must have, understood all different types of ML, their pros and cons. I strongly believe this. So I'm thinking that you have very good understanding about ML. And despite, choosing the best possible ML and the best possible network, say 5G network that can support powerful data network, the complete transmission, the communication rather of the sensor data is very difficult. There are challenges. There are challenges related to the transmission, the complete communication of the sensor data to the cloud. So this can be responded by the EML, and this is why these days this has become very much emerging in the area of ML called as embedded machine learning. Still, a lot of research needs to be carried out. I have done one small assessment that what is the current status of the research in this particular topic. That also I will highlight in my next slide. So there are important factors when you compare between ordinary ML and the EML. The EML is nothing but ML embedded into the device. The ML which is deployed into the embedded system, that is EML. So there are factors, there are many factors. I have included some important factors here like power consumption. Anyone can easily understand this relatively high power requirement of radio transmitters or receivers. So what happens? So many times the data is, data is captured, then data is interpreted. That interpretation, the necessity is communicated to the cloud or the PC or the computer. Again, the action comes back. So many times these transmitters and receivers, transceiver systems are active. They're almost all the time active, helping in communication the data between the device and that is your system, electronic system, and the computer or the cloud. So therefore, there is a huge amount of power consumption when you go for ordinary ML. Ordinary ML means, conventionally. Ordinary means, I'm not saying only ML. It can be DL also, deep learning also. The point is how you are deploying. So that is one important aspect, the factor. Second is network cost. Network cost, overloaded networks and the cost of resulting data traffic. The network will be overloaded because that cloud is being used by a huge number of the electronic systems. They're all connected with a number of IoTs and sensor based devices. So therefore huge data traffic will be there. The network will be crowded, overloading will be there. That is another factor. Latency, I think it's very simple term. Excessive round trip transmission time for sensor data and feedback of actuator commands, especially for real-time applications that require a quick response. Say in healthcare or environment applications or any application where we are, we need quick response, immediate response. But some average amount of latency will always be there because of round trip transmission between the device and the system where the ML is running. The ML may be of any type, but ML is learning somewhere. So that latency is there. Then privacy is always a factor. We need to prevent external access to audio and video recordings from the industry system. So everything is going there in the cloud. So the concern related to privacy is always there. Other factor is security and safety. Risk of data and device manipulation is always there. So there are other factors related to energy efficiency, but these are, I think, the significant attributes which come into which are taken into consideration while comparing ML deployed conventionally and the ML deployed into the device itself. So for the simple sensor data, let us now move towards EML. How can we do it? Like you see here, one interesting diagram, like it may be application specific IC or FPGA implementation. What we want is, we want to embed our ML inside this particular system. So maybe for a simple sensor data, the data is very small, simple data. This can be done with standard microcontroller. And if you Google about the EML, in almost all EML and emerging applications, you will find the usage of some microcontroller or microprocessor. So what we can do, a standard microcontroller can be used, that can be used suitably for that particular ML, where the ML problem can be solved and the applications where the ML can be deployed, having some few number of channels, and maybe the sampling rate is a small, that is low sampling rate. But this is how you can conceptualize that a sensor data, the sensor data can be interpreted in the device itself, taking help of a microcontroller, where a simple ML problem can be solved there, can be executed there and the data which is captured by the sensor can be can be understood, can be interpreted. The data is simple. Even if it is more complex analysis, there is huge amount of data like image sensors. We know that image sensors, when we talk about deep learning, you all know it very well. Wherever image, video processing, come into picture, the deep learning CNN are the models which are always suggested. So for complex analysis such as image sensors, deep learning accelerators, ASIC accelerators. These accelerators are available, which are connected with the device, which are associated with the device. Those accelerators help, and there are some models of accelerators which are already available. Those accelerators are utilized, and even for complex analysis, the ML deployment and its execution is made possible on the embedded device. So for, say, there are other applications like speech processing. I have seen that you have a topic ML for audio signal processing. So say for speech recognition or speech signal processing, an accelerator core on FPGA. FPGA is, the module where we are going to use another accelerator, maybe ASIC accelerator, that may be a suitable option for high volume application. So for a given problem, the system requirement, how do we deploy these things? Because there are accelerators available, there are modules available, there are packages available. So how to make use of those packages and modules while deploying ML, modeling ML into the device. So we can begin with a problem, given problem. We can analyze the requirements of that problem, and accordingly, we can choose the appropriate algorithm and the best hardware or best possible hardware, best possible module according to the requirement, according to the suitable algorithm being chosen, can be selected. This is one application scenario where, what I was talking in previous slide, what is the requirement, the customer problem. Accordingly, you have to analyze the requirement in the customer problem, and then you can create and optimize the machine learning model that for this particular requirement, to meet this requirement, so to solve the problem of customer, what is the suitable, method for method of ML that can even help in learning as well as optimizing, maybe, classifying the data. Then selection of embedded target platform, which platform you want to work. It may be, implementation and integration or target platform that may be, related to these things. It may be microcontroller based, embedded GPU, or any other like ASIC, FPGA, or there may be integration to ASIC of the requirement, and accordingly that ML is deployed and executed. This is one scenario I was talking about. See, this is one simple diagram where it depicts smart environment monitoring, and this simple application employs a number of sensors for different applications. You can see this is when we talk about smart environment monitoring the environment smartly and intelligently requires a number of smart sensors and IoTs. But there are a number of parameters in the environment, when we talk about signal processing application of environment. So how the data comes, the pollutants may be many. So the sensors which are used in the smart environment monitoring system may be of serving into this kind of application, that is clean water, smart aqua sensor, and then different types of sensors, either to monitor water pollution or the quality of water or quality of air, quality of radiation, and so on. So when we talk about a smart environment monitoring system, it does not only require these kind of sensors, but there are many other sensors which are required. What is important in this diagram is, you see here the IoT devices, the sensors are all connected to one cloud. So using this cloud, using your app, where in mobile app you have a mobile device, you capture the data and you can find out, you can assess the pollution level, what is the air quality, what is the water pollution level. That can be done. You think about the farmers who want to access the soil quality, who want to evaluate the soil quality or the crop quality, this becomes little difficult. This becomes really difficult. So therefore, if we can have some smaller devices, electronic systems, those which can run on batteries or solar power and can have their own ML capability, is going to transform the agriculture, is going to transform the environmental sector, the agriculture sector. It will become smart agriculture, intelligent agriculture, like that. So what I'm trying to say here, that the dependency on the cloud or dependency on the PC is there, and the EML responds to the great extent addressing the difficulties. As I told you, there are huge number of challenges already being discussed in this area, and there is some amount of research going on, so that the difficulties which we are currently facing in the area of EML are also addressed and overcome. There is another scenario, you see emerging smart sensors for different applications. Remote sensing, you have a GPS and different applications where you deploy the sensors. For agriculture, for remote sensing, cutting edge technologies are there for sensing, to sense the data, to analyze the data, and and so on. So this is the application I was talking about, smart agriculture, right? It can be used for health and health monitoring of the crop, health monitoring of other things, temperature sensor and other types of sensors can be used to to analyze the quality of product, the quality of crop, and so on, the vegetation, non-vegetation, the classification, and so on. Other different there are multiple applications of sensors which are reported in agriculture area. So there is going to be very much useful if we can have the embedded systems where it also can have some ML ability. If you see this interesting comparison I brought, from the source I have already given here credit, that the miniaturization of sensors is becoming very rapidly increasing, and this supports our statement, supports the vision, supports the goal, big dream that the embedded devices having EML are going to create transformation in the engineering and science applications. It may be related with air quality, as I have included one diagram here, is actually smart home. When we talk about a smart home, it is related with water quality, smoke detector, air quality, fire detection, and so on. Fall detection, whether there is any possibility of falling, the roof or something like that, some other object. So in all, such applications where the miniature sensors are there, the possibility of deploying ML or modeling ML into such devices becomes, realistic. So the EML on embedded devices. Is it possible to use analog and some mixed signal circuits to improve the efficiency of ML systems? This is what we want to achieve. Is it possible that analog and other devices which are there, and we want to improve the efficiency of ML which is there in those devices? And the answer is yes. And this is responded by EML. There is another diagram where you see the AI capability is there in the device itself. We can have embedded vision ML on embedded devices for application like image classification used in industrial IoT based application. This may be any application, not only image classification. The pictures are sent to server. This is generally the practice. Pictures are sent to the server for recognizing them, and with increasing number of sensors and the captured data, the images. We also talk about, I have seen one of the important topic is already there in the agenda, in your other topics, as edge computing. So we can use edge computing to address the increasing number of data, that increased data transfer rate and the communication bottlenecks. Edge devices are there. Those edge devices can be deployed near the electronic systems, and rather than communicating always to cloud or a system, we can communicate to the edge devices, and the difficulty related with the data transfer and the communication, because communication has become bottleneck. All the time we need to communicate to the cloud or a system. That bottleneck difficulty is addressed to large extent when you use edge computing. So we can do processing locally. When we use edge computing, we use edges. It can do the processing locally as close to the sensor as possible, and then only transmit actionable data to the server. See, this is the interesting thing. What happens now when we do not use edge devices? The data which is captured by sensors, say in an electronic system, you have 1000 sensors, and 1000 sensors are capturing all real-time data, and all those data are going to the cloud or the server. But actually, for the intended application, all the amount of data which goes to server is not needed. So what is the useful amount of data that actually can be transmitted as a actionable data, where some action can be taken by the server running the ML model, suitable ML model there. So this kind of thing is also achievable using the edge devices. To large extent, the difficulties can be overcome. There is another term coming as a CV. CV is it's a general purpose term, computer vision. It only mimics the human vision. In our human vision, we have human eyes and the brain. Whatever we see in the world, that is interpreted by our human brain. In computer vision, it has sensors, and the sensed data goes to the machine, where you have some computational algorithm that mimics our human brain. So the CV results very high performance in the cloud. You can run any CV algorithm, any kind of CV application. So you can get very good performance in the cloud. But the end-to-end edge devices are just used as sensors that serve raw data to the cloud. The same concept is applied to IoT devices employing the CV. So the difficulties currently being faced, in these applications, some amount of, I think I have already explained this statement, the first one in the previous slide, some amount of irrelevant data sent and stored into the cloud. Irrelevant. That is actually not actionable. It's not meaningful. It's meaningless. So some amount of data which is irrelevant, which is meaningless, is unnecessarily sent to the cloud. So you see here, there is a constraint related to bandwidth, there is a constraint related to time, and there is constraint related to storage. All these three aspects are related with the first point. The next one is high energy consumption of edge gateway devices caused by continuous wireless transmission and communication, and that also high energy consumption is there, so that also causes decrease in the life of battery which is used in the device which is present nearby some edge devices. The next point is there are issues related to data privacy. I think this point already came in our previous slide. Issues related to data privacy, security as sensible data accessed by the cloud, and the cloud in one way becoming as a bottleneck, a single point of failure. Communication and processing, everything is happening there. If there is any difficulty in the cloud, so that becomes a single point of failure where your system is collapsed. All those devices, all those applications which are served and connected with the cloud, the system gets collapsed. So that bottleneck system is there, and that can also be overcome. So what we can do in an application like image recognition, ML capabilities can be can be there in the edge devices and or the embedded devices, either edge devices or embedded devices. We are talking about EML, where we want the ML completely into the device, but other which is intermediate is edge devices are there, and to the edge devices the electronic systems can be connected. This becomes computationally intensive and challenging for embedded or wearable devices due to their constrained resource. They do not have much memory, they do not have much resource. So therefore, when the task becomes computationally intensive, the situation becomes challenging. And sometimes you find there is a term which is used for EML or edge devices constrained resource, technique. The resource is always, constrained. See, this is an interesting comparison I thought of bringing for all of you. I'm not saying that much has been done, and I'm not saying that nothing has been done. What I'm trying to say that you all people have attended a number of lectures. Many of you I know, have been doing greatly in the area of healthcare and signal processing using different machine learning tools, maybe in wireless network or a sensor network or maybe in IoT related applications. But actually we need to do a lot of research, combining the two aspects, that is ML as well as electronic system, and we need to aim at bringing ML into the device. So when you see the current scenario, you look at the scenario here, right? When I just tried to find what is the quantum of research which has been carried out, embedded ML, this is the general purpose ML. So when I tried Google Scholar, Science Direct or ACM Library, I have included only 4. I could, include some more, but I thought of including these important libraries. So when I found, there are only limited articles, significant articles which are reported. When you go for EML for healthcare, you see the number which is very, very less. Really, not encouraging. It's very discouraging. And when you go for EML for smart environment monitoring, because I'm targeting at these two applications, the EML is not at all my research area. My research area is, of course, image processing and then applying suitable AI and ML into image processing, particularly biomedical and medical imaging. But I thought of doing something, contributing something in the area of healthcare and a smart environment monitoring system, as I have been requested by South Korea professor to be part of his very important grant on smart health monitoring system. And I have also started contributing to him related to IoTs and the capabilities of IoTs, what kind of IoTs are suitably can be suitably used. So my point here, what I want to submit here is tremendous amount of research scope is there. Tremendous amount of research needs to be done so that more and more advances come out, and then we can get whatever we can overcome whatever challenges are there in the embedded devices where we are running EML. There are constraints related to the resources, there are constraints related to memory and the capability that can also overcome where that can be also overcome where a lot of research is carried out. So the embedded vision, let's continue. I thought of including that the status of research so that you can have some encouragement that because this is not a new area. What is new thing here is we are I can see that the department is Electronics and Communication Engineering who is organizing this program, but I know that many allied and interdisciplinary and multidisciplinary people are also joining this. But there are two aspects which we want to combine. One, there are some electronic devices, electronic systems, and we have understanding of signal processing basics and ML. So let's bring ML into these electronic devices and we'll start contributing something to whatever extent possible. This is how we can begin some amount of research in the area of EML. Maybe we can begin with a simple Arduino board or Raspberry Pi, as one of my UG student has done some work using Raspberry Pi. Actually, I wanted to get a lot of her results, but I did not get due to some limitations here. But I have included in the last some practical results which my student got through Raspberry Pi related to object detection on the real-time data. So we can begin with choosing one suitable package, suitable one suitable model, and then whatever data set can run, or we can try with our own data set, real-time data set, and can try running ML in the small electronic systems which we can think of using it for either water quality measurement or health monitoring, or maybe related with some, plant and finding the characteristics of plant and so on. So when we say EV is embedded vision, it's nothing but it is extension of CV. CV is a computer vision, but again, as I told you, what happens? CV is nothing but ML and AI makes your sensory data powerful. It gets the capability to understand. It becomes computer vision. So what we want, EV applications are computationally intensive and require computationally efficient algorithm. So what we want to combine CV with embedded system. It becomes embedded vision, because for the people who are working with image processing, there is always vision, computer vision. So let the computer vision be combined with embedded device or system, then it becomes embedded vision. But it's not only related with the vision part. Any kind of embedded system can be combined with the ability, the capability, exploiting the capability of ML, and can be modeled there. So open source libraries are there like OpenCV, other image manipulation libraries are there, which can be chosen and can, one can try on embedded devices. EV is a actually combination of a number of fields and the design constraints, and the entire execution on EV is done on the embedded device, and only the meaningful data is sent to the cloud server in EV. So I was telling you about edge, where only the meaningful or actionable data can be sent to the server or the cloud server. So embedded systems, I was using the term resource constrained systems. How can we define embedded system? The embedded system is an electronic system having ML capability, resource constrained systems designed for a specific task or tasks running on a controller or a microcontroller that, of course, needs to be always optimized for size, cost, power consumption, reliability, performance, and many other metrics. There may be many other performance evaluation metrics. So the embedded system can be defined or can be designed, and that's nothing but employing a controller. The suitable method or ML method can run on a controller for a particular, for solving a particular task. But of course, the performance can always be optimized either by choosing another model or another package. Things can be always optimized. That is what is the vision for EV, called as embedded vision. There is a popular term which comes, before you, in front of you, when you talk about EML. Tiny ML is a fast growing field of ML. You all understand what the meaning, the tiny carries. So it's a fast growing field of ML, that applications that includes hardware dedicated to integrated circuits, algorithms, and software. This can perform on-device sensor tasks. The tiny ML, is the module here. It can perform. This may be, related with Arduino or some other package. So the tiny ML can perform on-device sensor tasks. The sensor may be related with vision sensor, audio sensor, or other biomedical sensors, EEG and other types of sensors. And not only, can understand the sensor data, rather it can give you a lot of analysis of that sensory data. So for example, when we say Alexa, sing a song for me, or okay Google, Alexa, okay Google, these are the devices that respond us instantly. Of course, they make use of ML, they make use of cloud, they respond instantly. We want our embedded devices, to respond quickly, to respond instantly for our different services and the applications. So can we have tiny ML? Can we have tiny DL, that is DNN or DL, that can help us in designing and modeling the embedded devices that can respond to our need, that can solve the task as soon as possible. So we do not need to wait for the device to send the voice. I have already told you this, to the servers where it is processed and the information is retrieved. So the tiny ML employs models that can run on small, low powered device. Tiny ML, it can be a name of any model, that can run on a small, low powered device like microcontroller, and can enable low latency, low power, low bandwidth model inference at the edge devices. Of course, we cannot have higher bandwidth, higher power, high latency. Low latency is the beneficial thing. Power requirement is low. It can run, it can operate just by using a small battery, or even solar power can operate that particular device. So the model, suitable model can be deployed there, can run there on the controller like microcontroller that does not require much power and is small in size, and that can help us in understanding the data quickly in the deployment sites only. We do not need to wait for the decision or action which is responded by the cloud server. So let's have some comparison. A standard consumer CPU or GPU that consume approximately some 65 to 85 or 200 to 500 watts respectively for CPU and GPU, consumer CPU and GPU. But a microcontroller consumes power in million microwatts. So the power requirement there is also less. So in one way, the world is talking about the reduction of emission. The world is talking about energy conservation and saving up energy. So energy efficient implementation can also be achieved when we go for the implementation of the embedded device, where we can get rid of the CPU and GPU all the time for our intended purposes. So the low power consumption enables the TinyML devices to run unplugged on batteries. This reduces the latency of the output. You can easily understand the latency problem is solved, and the model runs on the edge. Thus, the data is not stored in any server, and therefore, the issue related with privacy or the issue related with security of your data is also addressed to large extent. So like, okay, Google or Alexa, you can share the examples of TinyML. I'm not saying that ML is always deployed at the end device, edge devices. That I'm not saying, but these are the examples of TinyML that has capability to respond and to responding instantly to the task or to the problem or the problem statement. So when you see embedded machine learning and IoT devices, you can have one microcontroller unit here, this particular part that has low power, low latency, lightweight, high performance, and the real-time data source is there in the physical world. And the physical world is the real-time world that is being captured or acquired. The data is acquired through the with the help of IoT devices. So let's understand what I'm trying to tell you. Edge is not an IoT, right? Edge is not an IoT. We must not make a mistake that all edges are not IoTs, because you see the clear-cut separation here. Cloud is somewhere here. Cloud has a data center, or that capability is there itself. So there is a cloud, there is a data center, and these are the edge devices where basic analytics can be done. Some optimization can be done, some machine to machine, the communication and processing can be done. But these are the devices, these are actually the IoTs, Internet of Things, used for different applications, or either for communication or for transport or for manufacturing or energy and other electronic systems. There are different applications where the different IoTs are connected, and these IoTs are not edge devices, what I'm trying to say, right? So edge devices are actually helping to the IoTs, so that we are getting benefit of latency problem. We are getting benefit of this huge communication time, means latency time, and of course the overload in the network, and many more. Even if you are overloading the network, bandwidth utilization is large. So you are also getting efficient bandwidth utilization when you are employing and using the edge devices and serving to your IoTs. So the applications of TinyML, like, there is a very popular term you can find when you just Google EML, you will find TensorFlow line. It has capability of training, distillation, quantization, encoding, compilation. All these capabilities are there in the TensorFlow line. And this is also a package for TinyML. So TinyML can help monitoring the machines in industries for different applications, and also can help in predicting the faults in the different areas or different sections of the industry. The predictive maintenance, which is possible by using TinyML. TinyML can be deployed at different areas, which are feasible, where the components or the stages can run on battery or some solar power. There we can make them freely working, independently working, running on certain model and helping us by predicting certain faults. So this kind of predicting maintenance, that leads to cost saving. Of course, that leads to cost saving. For example, like Ping Services, there's a startup in Australia that uses IoTs that monitor wind turbines. They have this kind of app that startup that uses IoTs for monitoring the health of wind turbines. So TinyML can detect the spread up. There is another area, I could see in your agenda a number of lectures. I think 2 to 3 lectures are there related to healthcare. So healthcare is actually very much emerging area where the IoTs and smart sensors are used popularly and hugely. So it can detect the spread of mosquito-borne, diseases or any kind of disease such as dengue, malaria, by detecting the mosquito breeding conditions, and it can run on solar power as well. TinyML based apps we can have that can help in detecting the diseases in plants just by taking a picture and running ML models on the device using a TensorFlow structure like this. So the the quality of the plant, the disease in the plant, the disease in the crop. I was talking about smart agriculture. There, the poor farmers suffer with a number of diseases, which are there in the crops, in the plants. So that analysis, and then accordingly, they can get the remedial actions to be taken. What kind of disease, how much it has affected, what kind of remedial action can be taken. That kind of planning, can help the farmers to get their better productivity by using the smart techniques and smart devices. So it's going to, if it comes at that scale, and I don't think it's a difficult task. It's going to be in large scale. So it's going to transform the agriculture. It's going to transform the remote sensing sector. It's going to transform the weather forecasting sector and many other areas where signal processing is in the center. You have a signal, you have a data in some particular electronic system. You want to get it interpreted using suitable ML package. So how to use, just by using one example I'm trying to explain. Many of you might have exposure to all these things, what I'm trying to talk about, because the idea of bringing this topic is to just get a good exposure to the topic and the research potential, knowing about the research potential and what could be done. That is the main idea. So to begin with, the Arduino, there are different types of Arduino boards, we know that, but there is a board Nano 33 BLE Sense or similar kind of board can, or suggested hardware where we can deploy the ML models as, on the edges. On the edge devices are there. They have some, the memory capability. There we can connect with the Arduino board and the ML can be deployed. This can use 32-bit ARM controller or any other controller, say ARM controller that can run at 64 megahertz, having certain program memory or certain RAM also is there in the microcontroller, so that some amount of RAM is always needed. So that much is there in the microcontroller that will help us in running the model. And this implementation can provide enough power to run the tiny models. This particular model we can run a number of models on such microcontroller. It includes this implementation includes Arduino board. This has been tested by our students here as their minor projects. They have done, they have tried to do a number of. I'm not talking about ordinary sensing it and analyzing it. They have actually made use of certain packages and connected with the Arduino and the camera and tried to analyze the data which is captured by different types of sensors. So that is being done, and that has been done by our students here also. So based on that, I have included this. So it can include brightness sensor, proximity sensor, gesture, motion, vibration, orientation, temperature, humidity, pressure, and other different types of sensors are included. Of course, digital microphone, Bluetooth devices. So Bluetooth low energy, actually, BLE stands here for Bluetooth low energy module are also there. So TensorFlow Lite is the most popular community support. We were talking about TensorFlow Lite in previous slide that supports ML framework. A number of models are there, and you can choose a data set and a number of ML model, a suitable model can be chosen from the framework and can run on this TensorFlow Lite, and it can be deployed on microcontrollers. So microcontrollers are used to collect the data, and using tiny ML, the model, we can leverage the data to build better product. There are, because microcontroller is not a problem at all, and that too we are getting, there is an emergence of good and better microcontrollers for different applications. So there are over 250 billion microcontrollers. If you find out in Wikipedia, you will find some 250 billion microcontroller units are there, and is day by day rising exponentially and rapidly. So say on FPGA, ML, we want ML over the FPGA. The neural network can be modeled over FPGA directly towards, and that can reduce the power consumption. TeraDeep is one example that aims reducing power consumption by offloading intensive computing tasks to hardware running on the top of FGA. Another company like Movidius released a development of kit designed for porting CNN to EV processing unit, that is embedded vision processing unit, and the name is Fathom Neural Compute Stick. So this is one, there are two examples related to ML on FPGA. There is another one, that is ZVoice, is a deep learning smart camera pack. This is being used by the researchers to carry out a number of research contributions related with the EML. So this actually is deep learning smart camera pack that has 6 core processor and can handle up to 13 trillion operations per second. This is being written here as TOPS, trillion operations per second. So that capability is there in this camera. It's a partner of Google Coral that brings the latest capabilities in embedded deep learning, embedded ML only, but we are calling it as a EDL, embedded deep learning. It includes video sensor, quad-core CPU, USB video and serial port, all together in a tiny, small package. And you can see here the dimension of this package, and packages of smart camera. A micro SD card is loaded. You can load a micro SD card there with open source CV algorithm, a suitable open CV, algorithm like this, darknet or TensorFlow, and can be connected with PC or any Arduino board, and then you can deploy the ML you can exploit the capability of DL and can implement an electronic device connected with the Arduino, using a suitable sensor or any other input device. So these are the two examples from that smart camera applications. Like, it detects and identify the multiple objects in complex scenes. Multiple objects can be detected, and there is a TensorFlow. It can identify 1,000 different object types up to 83 frames per second using deep learning. So such a small application has already been included related with Raspberry Pi that I will talk about later. So we need powerful CV, right? You see here, there is an interesting diagram. There is an elephant that is seen by our human eyes. It goes to our human brain, that sensory data, and we interpret this object as an elephant, correct? So we are talking about a smart camera. We need powerful CV, AI, and deep learning based camera, and that GVoice can run DNNs that can recognize 1,000 different types of objects in real time. So general purpose standard camera captures video. It sends the video to human being, as I explained, and human brain is used to interpret what the content there in the video. Whereas this smart camera can capture a number of videos, can process the video and interpret the content, and also can send interpretation to the human or robot or any other computing or computer applications. So it's not only that it is communicated to the device, but it can communicate. It can be communicated to anywhere, wherever we want it to communicate. So it's a smart camera. It has those connectivity through which you can connect an application, and that data interpretation takes place in the electronic embedded system. So deep detection. Deep detection means employing DNN. You are able to detect the object. And here in this diagram, you can see there are faces in the diagram. And what is important here is even quantification. How much percentage, that is 97%, 98%, 96%, is also being predicted. And this is very common thing when we talk about ML, right? When we say soft computing is a powerful technique that is a general purpose term that has different dimensions, like neural network for training, AI for understanding and knowledge acquirement and knowledge representation, and then genetic and other algorithms for optimizing the thing. And there is a fuzzy logic that aims at addressing the uncertainty, because in object detection it becomes very important that how much is the level of certainty, that has to be also determined. So this is being done by using it's detecting, recognizing a number of objects and scenes using suitable OpenCV DNNet, and module runs on the object detection network using OpenCV library. It can analyze a scene and can produce a number of bounding boxes, you can see here, around the detected objects, and together with various labels and identity, how much score is there, how much score, how much confidence score, or you can say certainty score, any name you want to give. That metric can also be, can be estimated, can be determined by using this. I'm just telling you the application of GVoice. There are many applications, like deep detection is one. There may be color filtering. As I told you, it can be connected with any other Arduino or any other kind of board where you connect the data. There is a serial, there is a card, SD card, where the data which is related to understanding the data is stored, and that can be connected with Arduino, and you can understand the scene or the data. So this is another application like color filtering. There may be numerous applications of image processing related to either detection, color image processing, color image enhancement, color filtering, color correction, image restoration. Many other things can be implemented using. What is important is we can sense the data, we can capture the data. What do we want to do with the data? We want to classify, we want to enhance, we want to filter, we want to get only the edges of the images, edges of the colors. We want to separate the color components. Accordingly, you can use the suitable classifiers and ML models, and those models can be deployed on the electronic systems. So if TinyDNN is deployed into GVoice, it can integrate new functionality into device, and it can exploit the capability of TinyDNN, so that the TinyDNN is integrated inside the Linux kernel or any other. In an ML problem, the implementation task can be broken down to training and inference stages. There are two stages in this implementation. One is named as training, and other is named as inference. The training is computationally intensive. Of course, in comparison with inference, the training of classifier is done on the board virtual machine using its CPU, is because of being computationally intensive. The network can be trained using, again, it's a normal thing. When you want to train a network, there are certain parameters which you keep in your mind, like how much learning rate, what then if you want to achieve a suitable learning rate, what is the step size required, that can determine the convergence of neural network, so that it can converge and finally it can classify or understand the data. It can train the data. Then of course, number of epochs, batch size, etc., etc. So when you train a network on this model, of course the learning parameters can be set, the training parameters can be set, and the network can train there and can have impact. A new module is created. It can be created using a create sample module script that is there, which creates a default pass-through module with given module name object detect. We are talking in context with object detect. So this diagram tells about hardware as well as software part. So I was telling you that ARM's GPU is there, DDR RAM is here, then camera interface is there. You can connect camera in the hardware part. Micro SD can be inserted there. You can get your data. An embedded controller is there. Host computer can also be connected, and this is related with software framework related with video output and understanding. You can connect with embedded controller and suitable software. That package can help us in understanding the movie or the images which are captured by the camera, which is connected using this camera interface and the hardware available in the device package. So let's summarize this particular part and we'll go to the next part quickly. So the dependency-free ML framework with hardware optimization that realizes practical applications of ML on embedded devices. A lot of EML research, I have already mentioned this, a lot of EML research has to be done, needs to be done to improve accuracy with unlimited resources, which are subjected to energy and computation budget constraints. There are two important constraints related with energy and the budget. So an automation is needed to port the classifier onto the embedded device. This can be anything, not only the classifier, but we want an AI or ML to port into the embedded device, and that has to be done automatically. For that, the issues related with energy and the computation budget are to be addressed. A focus on optimization of DNN that runs on embedded devices is needed by optimizing for the measurement or the precision impact. The optimization can help the porting process and also in reducing the computational complexity of the network. So a suitable classifier, a suitable optimization can be used in order to reduce the computational complexity associated with the network. And as I mentioned again and again, the work could be done in the direction of power optimization by changing the algorithm to fine tune for specific need or a specific hardware. That helps in reduction of memory and computational footprint of the network. So this is written in bold because a lot can be done here in order to address the issues using suitable optimization technique. So let's talk now about some smart sensing and the role of EML in smart sensing. In the we have, I think, another 30 minutes with us. So in 30 minutes, I will try to talk about smart sensing, and then we'll be going into the TinyML and for Raspberry Pi implementation slowly. So smart sensing, I think we do not need to repeat everything. Again and again, we have talked about conventional sensor. You have the application associated, whereas in a smart sensor, you have a data pre-processing. And in the smart application itself, the model becomes smart, and your model can interpret the data which is captured by the sensor. And we call this, therefore, as the smart model. So how can you train this? There is a data pre-processing and there is a model training. I believe all these stages are very common. You can use classifier or regression technique, whatever. So this is not an a very different thing than the ML. When you pre-process, you get a feature map, and the feature vectors are trained. It's a common thing. What is important is we want this to be run, this to be executed on the device, the embedded device that we want. That is what is called as a smart sensing. When in an application, when in a electronic system, the sensing becomes smart. That can make use of wearable sensors, wearable devices, maybe for your biomedical applications like EEG, ECG, and other signal capturing, or on-chip neuromorphic edge computing that involves signal processing, models, algorithm, the biological materials and other things. And then related applications are human machine interface, HCI, health monitoring, related with toys and games, disease diagnosis, robotics, and etc. etc. So the important term which is coming across in all such scenarios, is smart sensing and responding to the need, responding to the requirement as quickly as possible. So the energy is coming very often, frequently. So let's talk about energy efficient EML related with smart sensing. How do we get energy efficient EML? So I was trying to get some research papers on energy efficient EML. Again, the research on energy efficient EML is very much limited. Lot can be done to implement to come out with energy, to address the energy efficiency in the EML technique. So this is one small, a simple or a typical diagram that depicts EML. Then energy efficient techniques, you can use certain parallelizes, parallel architecture, parallelism. You can use certain approximation, what is called as approximate computing, the using parallel concept, parallelism concept, network sparsity. There are some techniques which are suggested in the literature, and the technique can be used in order to make the EML as energy efficient. So if it meets the requirement of your application, then you can just embed it, efficient embedded implementation. Otherwise, you can again go to EML, see the requirement, choose a particular technique, and make it energy efficient. And when it becomes energy efficient, that can meet your requirement, means the power, the energy which is available there in the devices for a particular duration, where the device is desired to respond, is able to perform, you can say yes. Otherwise, go back and again make your EML more energy efficient. So the embedded autonomous electronic systems, they have IoTs, wearable devices, biomedical systems. The system usually hosts sensors. In any autonomous electronic system, we have sensors. Again, the sensor hosts a number of channels, like you see in case of biomedical image processing, we use the term channels. There are so many channels through which a number of or huge amount of data can be captured. We put biomedical sensors over the head, over the scalp, and with the help of a number of channels, we capture the data. So there are a number of channels, input channels, and those channels related with tactile, the touch or vision, according to the need or the application. And these sensors can be coupled to electronic computing unit, where some amount of computing can take place with the help of your controller. And of course, that will help in extracting the information. EML algorithms, they pose some challenges. The EML algorithms which are run, they pose challenges in terms of hardware resources. Therefore, we call them constrained resource and energy consumption due to high amount of data processed and computationally demanding method. Because whatever ML model that you run is always demands for more and more number of computations, especially when you have more data, high amount of data. So when high amount of data is there, of course the consumption of energy is more, and consumption of energy increases because of computation, the number of operations, the number of operations. If it goes high and high, the energy requirement will become more and more. So the energy efficient techniques, I think some techniques are included here. They are only written, like parallelism, approximate computing, network sparsity, it's a kind of, say, related with image. You can say we can use a technique called as what is called as fractal compression kind of thing, and some similarities can be utilized, and we can compress the data kind of thing can be done on EML system, and that can be used to improve the energy of efficiency. So the energy consumption takes place during runtime of the algorithm in embedded devices, such as computing energy, IO operations, necessary energy for memory storage as well. You're storing something in memory, or you are performing IO operations, energy requirement is there. And since everything is being done there, the final actionable data, you can also say the final actionable commands are performing the task standalone. It's not being communicated between cloud and here. So that kind of energy consumption is there at the end of device itself. So that efficiency is therefore considered as a crucial factor in applications such as portable devices, medical IoTs devices. When we talk about telemedicine, telemedicine or tele-healthcare, where you have electronic systems that can capture different human body parameters, right? And where the doctors cannot go in rural areas and other areas, you have medical IoT devices. So energy efficiency becomes extremely important there. Energy requirement and the efficiency becomes important factor for that. So therefore, the integrated circuit must embed ML instead of, such ICs must be embedded into ML instead of, more power requiring kind of microprocessors in order to meet the low power budget requirement and constraint or limitation in wearable or implantable devices. Improved energy efficiency that increases battery life. Of course, it will increase and more extended. See, when do you get more battery life and your energy efficiency is more and more of then more or extended functionalities can also be implemented, can be achieved in the model. Latency, as I told you a number of times about latency, that depends on number of operations performed in a unit of time, such as operations per second or floating point operations per second, and that affects the energy operations, energy efficiency. More and more number of operations, latency will be there. If both the factors are affecting the energy efficiency. More so memory subsystems which require significant time. There may be many memory subsystems required in the different controllers. So that also requires significant time and energy in computing platforms due to the frequent high data transfer between processor and off-chip memory. So there are two scenarios which are given here. You see embedded RAM is there, and here your RAM is being used externally. So in case of embedded dynamic RAM, on-chip RAM, you connect directly with the logic, whatever logic you want to implement, and here you connect with the logic chip by base bonding and small bandwidth utilization. Here your utilization is more. So the DRAM or the memory can that with having limited capacity is employed for storing a high amount of data and parameters, because you have training data as well as training parameters such as weights in DNN, and of course the training vectors as well, like feature vectors in support vector machine. Higher the amount of data, more challenging the memory becomes. So the memory requirement, the selection of memory, the embedding the memory is also related with the amount of data. You have limited capacity, you have limitation related with the memory embedding into the device as well. So the algorithm, the next term coming here is algorithm complexity, that is related with the computation. It depends on number of operations or instructions executed in embedded space. The ANN requires energy consumption less than SVM, since the ANN model takes 5 times fewer operations than SVM. So it's so simple as the statement is. The performance study of ML algorithm depends on number of layers, also number of bits, and memory storage and number of operations as well. So these are the factors that affect performance. I don't think these are such novel statements, other than the statements related with the conventional implementation of ML. So we need to see processors support some significant features like quantization, sparsity, so that we can get the energy efficient model. So that by employing the quantization, parallelism, or sparsity technique. For example, there are different architectures. We can have a number of architectures of CNN, but the one which is having lowest complexity, say that there is an architecture that has there is an architecture which has the least or smallest complexity, can be chosen for that particular application. So the use of the model, arithmetic model, can aim to develop energy efficient and high performance ML algorithm. The conventional multiplication, when you talk about approximate computing, there comes an important term called as approximate computing when we talk about EML, especially when we are interested to have energy efficient EML. So the conventional, the traditional multiplications, the traditional multipliers, the ordinary multiplications, they take and they consume a lot of power and energy. So there are ways by which that effective number of computations can be also decreased. So conventional multiplication is replaced by using some shift and add operations, and the power consumption can be reduced by up to 18%. Of course, there may be some reduction in the accuracy, but not much. So if it is under the or below the allowed range, below the tolerance limit, because after a certain value you can compromise on the accuracy. But if the accuracy reduction is very less and you are getting power consumption reduced by much value, you can replace by some other alternate operations, computations. So the energy efficiency can also be improved by 45% after implementing the multipliers using the logic minimization approach in neural network. The ordinary multipliers can be replaced by these kind of operations, specific operations, and we can achieve energy efficiency up to 45% as well. So approx AN is a name for approximation. Approximation, when approximate computing or approximate multiplication or approximate operation, that can be applied for both computation as well as memory accesses. For an embedded DNN, this convolved net processor, convolution net processor achieve archives efficiency up to 10 tops per watt at the same throughput. So there is one more, statement related with pruning. We are talking about parallelism, sparsity, pruning, the techniques that can help in achieving and implementing the energy efficient EML. So pruning up layers of CNN achieve 70% of reduction in power consumption. And one such example is given here, right? And this is a very simple example where you can say a kind of convolution is taking place over the image, and so much of similarity is there in the image. So you can say some kind of compression, some kind of fractal reduction, some similarity reduction can be done, and the operation can address in can help us in reducing the effective number of operations, so that we get the implementation of EMLS energy efficient implementation. Approximate computation is a term that is used in image. CNNs are used in image recognition, video processing, NLP, other applications, which are computationally intensive and resource consuming. Performance is limited by memory when we deploy on embedded system, because we do not have that much memory in the embedded system. So selective binarization or any other kind of approximate computing technique can combine the layers with different precisions to help to achieve improved speed and accuracy. Using a Tino YOLO CNN with drone object detection dataset, there are different datasets available. We can achieve some improvement in runtime performance of the system. And then, as I told you, quantization and other techniques are there that can help us in getting lossless network, which is designed by using approximate multiplier. I have given one example of approximate multiplication in the previous slide. So this diagram tells about some more thing about approximate. I think we have already seen this diagram, but here it has been extended. We have some inexact circuits after applying the approximate computing methods. Either those multipliers, algorithms, or architectures are circuits that make inexact circuits, which are approximate circuits, not the exact one. And if now the quality is met, then we can again embed EML in terms of energy efficiency. Otherwise, it will go back, and again we can use certain approximate computing and can again improve. Of course, there will be some quality metric that will help us in assessing the energy efficiency, whether the total consumption is reduced or not, total bandwidth utilization is used or not, total effective usage of memory storage is decreased or not. Some similar kind of metrics can be used, and we can find out the the quality of convergence. Meeting quality means convergence here. So Such net is a set of multiplication less CNN. Multiplication less CNN, the CNN where we do not have those ordinary more and more number of multiplications. Rather, the multiplications are replaced by the approximate, operations. An approximate method is directly applied on the operators rather than operands as a classical model. So you see here, this is another interesting comparison between conventional computing and the approximate computing. Here, you can get very good accuracy. Very good accuracy you can obtain in conventional computing. But we, at the same time, want good performance of the ML, and good energy efficiency as well. So you can sacrifice to some extent over the value of accuracy, but performance and energy, are also improved to significant level. So this is achieved using approximate computing. As I told you, I'm not an expert of approximate computing. This is a terminology related with soft computing and signal processing. We have to choose certain operations and the multipliers in such a way that your performance metric is improved in terms of energy efficiency or other performance parameters. So this particular slide talks about FPGA platform. We know that FPGA is divided into Xilinx and Ultra, so let's not talk about the description, where the model can be converted here, FPGA model, where you can have inference result and inference database. So the database and the inference result means either the classifier result or optical detection result that can be, obtained here in this particular place using FPGA or other suitable platform. So I'm coming to the final part now, and we'll try to quickly finish the detection part. So as I told you, this is again available, right? Object detection and other applications are already available. Open source, you can find the packages, you can find different modules, you can choose appropriate ML model, you can choose appropriate data set and can run. And of course, you can always try to optimize the performance of those models and packages by using suitable approximate computing or some parallelism or similar technique. So this is object detection application using Raspberry Pi 3, and TensorFlow Lite model was used for detecting the object, and a kind of embedded vision, right? A computer vision where you have ML embedded into it. And you see here, there is a bird, there is a squirrel, as we have included one interesting diagram in the beginning, that what actually is the object is being detected or recognized as well. And then the percentage, you can say the score, confidence score or identity score, whatever you want to say, that is also being, done. And you know that it's all possible because of your ML capability. You can detect something, using a long program without ML also. But when you have more and more amount of data, you cannot do it. So you need ML, and the ML can help us in detecting, recognizing, as well as classifying, as well as the quantifying the score as well. So yeah, so this is one diagram which was used also, which is the highlighting the different objects like cow, person with the score level. It can be seen on the image, right? And this is the work related with the object detection itself. That is, cow is there, 64%, 59%, and here it is 51%, right? So based on, you all know that how the detection or recognition, works by employing the suitable features, by getting different types of features from the images, it results to the output. So there is nothing new. What is new is choose a model, choose a product, choose a package, and try to run that model in a package. And in maybe with the Arduino or Raspberry Pi, there is a camera. Connect the camera, get the real-time world, and interpret and classify. This is one application, but there are many other applications like audio, speech, where one can test the different models to respond your devices instantly, as quickly as possible. So there is a term TensorFlow Lite. Huge, information is available on TensorFlow Lite. Correct. So it's nothing but a light-weighted ML model that is trained in, light-weighted ML model is trained in this framework called as TensorFlow framework. And the trained models can be converted into these models, and that can infer edge devices such as mobile phones. Your edge devices may be your smartphones, mobile devices, or single board computers, microcontrollers, or IO devices. Those devices can also be, your edge devices, and they can further serve something. You can capture some real-time data through mobile phone camera or your IoT devices, and mobile phone or IoT devices can respond accordingly in the form of actionable data, decision, or some suitable commands related with specific applications like robotics, computer vision, or your image processing applications. So it performs optimization on trained models during conversion. It performs optimization on trained models, the model which you train. When you convert the model into, into your device, as edge devices have less memory storage and less computation resources, we all know it. So TensorFlow Lite supports size reduction, latency reduction, and hardware accelerator compatibility. So you can, understand that edge devices, we know that already they have capability. Edge devices, they already do have capability of the computation, processing, and decision making, converting the data into some meaningful or actionable, outcome. But the tensor light kind of framework supports the reduction in size, the latency reduction, because latency is the most important factor in such implementation. And of course, hardware accelerator, which we are talking about, ASIC accelerator or DNN accelerator. So hardware accelerator compatibility is there in the TensorFlow Lite module. Optimizing size or latency that causes loss of accuracy. We have already seen one diagram. When you address the issue of size or latency, when you recover some amount of latency and size issues, then it definitely causes some loss to the accuracy to some extent. And that optimization includes quantization, pruning, clustering, and other techniques are there in the optimization process while optimizing it. So I think these terms, no round trip to the server is nothing new. It's a common thing related with EML. So it's there in TensorFlow Lite. This diagram I have borrowed from the TensorFlow Lite data, open source information available. We train a model, we convert the model, then optimize the model using suitable technique, deploy the model at edge. What are the different edges which are possible? I have already given the example, and then that can be deployed either on Android devices or Linux based or microcontroller or some iOS based devices. And then the final inference at the edge can be, outcome can be delivered to the outside world for a specific applications. So in such a framework, and if you go to this particular link, I think included in my concluding remark, you will find the detailed description, how to choose a model, how to train a model, how to alter certain parameter, how to optimize the model, how to, select a different model that can replace the existing model for better optimization. Everything is very nicely explained in this particular resource. One can go, and then those who are very much excited to integrate ML and electronic systems can start working, and it's a very exciting area. Me being a person of purely signal and image processing, I have started reading, studying about it, and to some extent, if you remember in the beginning, there was a diagram, smart environment monitoring system. That diagram has been borrowed from my own paper. That paper was contributed, published last year, and you can see that in just 1 year it has attracted I believe around 90 citations just in 1 year. So what I'm trying to say that it's very much attractive with smart environment monitoring, smart health monitoring. So to in that direction, how can we monitor the health, how can we have smart healthcare. So in these, very exciting areas, we can have some smaller electronic devices and embedded systems where we can begin with, people are talking about startup, government of India is giving a lot of support for startups. There one can begin with such kind of work, right? So that is what I want to say here. So no round trip is not a very uncommon thing, can work offline. It's a battery operated and that has ML capability. Computation is done there itself. So you do not need to connect internet for a particular device. It's possible. No cost on network bandwidth. You are not utilizing the bandwidth. You are using all those smaller devices and edges are being used. So you can simply, uh, save the bandwidth cost or cost related with network bandwidth. Network connections are power hungry, so that requires a lot of energy. So you are getting rid of utilizing the network hugely. So you are getting benefit of that energy efficiency as well. And this is what is the explanation about how one of my undergraduate student has implemented one small real-time application using Raspberry Pi. So an SSB model was used where quantized models use 8-bit floating point number representation, and with a kernel size that results small mode size and faster computation. And this is the COCO model, that is SSD network for object detection was used, and this was trained from the COCO image data set. If you Google COCO image data set, you have a data set, and of course you can connect your camera and then real time the data can be captured as well, and the object detection can also be performed. I will highlight that example also. So how to train and convert and run the custom TensorFlow Lite object detection models, different, like you see that SSD mobile net V2 quantized COCO model, which has certain how many bounding boxes it can have, what is the speed in a millisecond, everything is there. So you can choose appropriate model. So my student who is a, chosen this particular model has chosen and tried to implement with Raspberry Pi and implemented the object detection. Of course, it's not designing the electronic system itself, but yes, realizing the real-time world and connecting through the camera and then implementing a suitable ML and realizing suitable applications. So I said SSD model that runs a convolution network on input image only one time and computes a feature map. It's an ordinary process, you all understand. It's an ordinary step that you convert into feature vector that predicts the boundary boxes and classes classification you do based on feature maps in one single pass. So MobileNet is a lightweight DNN architecture that is designed for mobiles and EV applications. This is used as an effective feature extractor for object detection and segmentation. So SSD provides object localization while MobileNet provides classification. So both were used and the combination helps in object detection. The COCO dataset is an excellent object detection having 80 classes and 80,000 training images and 40,000 validation images. And some more descriptions about it is written, and that model is directly deployed on Raspberry Pi 3 model B, and the inference through Pi camera V2 was used, a camera was connected in the model. This is what you can see, Raspberry Pi, and there was a Pi camera. This camera we have, we are just using one object as a bottle, water bottle, just to detect it, but I will show one sample result in the next slide. So the Raspberry Pi has a better inference time performance than Raspberry Pi 3. In this example, 3 has been used. The inference time is only 1 frame per second, but Pi 4 can achieve around 4 or 5 FPS, frames per second. So it even gives better performance. But what was used by my student was Raspberry Pi 3. So training custom models on the platform is difficult due to PI's limited processing power, that is Raspberry Pi, and that can be trained on Edge Impulse cloud platform and directly deployed on Raspberry Pi. So directly modeling on the platform, there are limitations related with Raspberry Pi. It can be done on Edge and then deployed on Raspberry Pi like this. So you see, this was one. I hope it runs. Yeah, yeah, it starts running. So you can see that there are different objects. This is what my student is doing with that pi camera. The girl is holding a cup, and that classification is also resulted. Now there is a television is also being detected. The teddy bear is also being detected. The bed is there in her room is being detected, right? And what is FPS here? That is also being reported in the inference outcome as well. That is also being reported. So I think we will go to the next. Again, this is sorry. I think this also I can play for you. It must play. I'm trying to play it so that anyway, I think while trimming the video, something went wrong and therefore this is not playing. Otherwise, this is the student who has done this, and the person could be classified. And this is her room where the girl is sitting there. You can see and holding the different objects, TV in the same place, same room, and a small, real-time object detection task was performed. So let me, because I think we are coming to the end, and I hope that whatever time was allotted to me, I have utilized perfectly, and I
Sure, sure,
think
sure. You
after
utilize
this,
perfectly.
thank you so much. So I have, I think, come to the concluding remarks. The need to process data at the edge for faster data processing and achieve quick, reliable results has been growing. The need for this edge computing and giving the responses by the edge or embedded devices is very much growing because of the automation and the era where we are living now. That demand has been growing so much. So the research in microprocessor architecture brings an era of running ML applications on smaller microcontrollers, and the EML research is still in its early days. Even if you read a research paper of 2021, it says that EML research is still in early days. Of course, we have embedded devices, we have packages, we have ML modules, we have data sets which are running, but a lot needs to be done. So I know that many of you are very, very good in signal processing ML, and then with the some knowledge of sensor IoT and electronic circuit design, I believe that we can begin with realizing it, putting the ML model into the device and exploiting the capability of ML for a specific application. So I have given one research paper. It's a very nice research paper. Maybe if requested, I will send this PDF to all of you. An overview of ML with embedded and mobile devices, optimizations and applications is very nicely reviewed in this paper. The current status of review, what kind of MLs are deployed, what are their capabilities, what are their limitations, are all highlighted very nicely in this particular paper. I think this is published in 2021 only. So with this, I think I will only again say thank you to the organizing team, Dr. Sachin, for having me in this program. And I hope that I could do justice to the topic, though I am not a, very much active researcher in this particular area. But I thought of bringing this topic so that an excitement can some positive ripples can come in the scholars and they can start doing research in this area. So that's all. Thank you so much.
Any question from the side of participants? You can also type in chat box.
The last slide where E equals MC square written is actually very interesting. Those who are, those who can see that is a interesting equation, right? You can later think about it. E equals MC
Yes,
square
sir. Yes, sir.
is very much encouraging to all the researchers and the students. Let me close the otherwise.
I think, sir, there is no question. Really, thanks for the informative session. Okay, can we implement without hardware in Linux? One question is there in the chat box. Sir, you are muted. Sir, sir, please unmute yourself. Sir, there will be a option at the bottom. Sir, can you unmute yourself? Sir, can you unmute yourself? You are not able to unmute. Okay, okay, okay. I think there may be some sudden mic disable. Okay, okay. Suddenly mic disable. So, okay. Yes, 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 yes. So there may be some issue. So because of that, sir is not able to unmute himself. So, sir, there can you type in the chat box for the answer? Like, can we implement without hardware in the Linux? Or sir, you can rejoin again, and in that condition, it may be the sort out. Okay. Yes, there are some models we can implement on the Linux also. Okay. Any other question from the side of participant? And sir is sharing some link, so please go through that link. Sir has already included in the PowerPoint, so you just follow the presentation. We will also share the recording, so you can check over there. No, sir, no, sir. This is just sudden issue. And really, thanks for the informative session. And the way you do the amalgamation of embedded field with machine learning and computer vision, the new field like embedded vision. So it's really motivates the participant to work in this particular field. And in the beginning, you have mentioned that you love the images, and I have seen that in each of your slide there is a image which is telling the entire story of your presentation. So really, thanks for that pictorial representation, and I think all the participant and I also will be beneficial from your this research presentation, and I will also try to work in the this new field like embedded machine learning, because you have shown the comparison that in this particular field only few researchers are working. So it's really a attractive field. So thank you for this nice presentation. So this is the end of this session. Thank you, sir. Thank you.